Welcome to Study Loop.
Hi everyone, thanks for joining me today. So what we have is we're going to be looking at a problem that looks at circular motion, work, and kinetic energy. And what we're given is a mass that is moving about a circle of radius L that is given a velocity at point A. And what we're asked to find is what is the minimum velocity at point A that should be given to the mass such that it can reach point B if the if we have a rope or if we have a rod. So I'll call that AO. So if AO is a rope, what is going to be our V0 min? And if AO is a rod, what's 0 min? So first we're going to look at this situation as if we were looking for, as if AO is a rope. So I'm going to do this as A, so I'll call this for rope. So let's think about this, right? So if we're going to do a rope, that means that the mass, when it reaches the top of the circle at B, the tension will actually be 0, all the taut in the rope will be gone. So if we were to draw this as a free body diagram, the only force that we have that's going to be acting on the mass is its own weight. And if we write this in terms of Newton's second law, this is going to be weight is equal to ma. And in circular motion, this is going to be weight is equal to m times v squared over L. So we know that weight is actually just equal to mg, so these masses cancel out. So in this case, we see that v squared is simply L times g. Now, we know that we're going to use kinetic energy and work in this situation, so let's go ahead and define those. We know that the kinetic energy at A is going to be 1/2 m v0 squared, and the kinetic energy at B will be 1/2 mvf squared. So let's look at this in terms of work now. And we know that the work from A to B, we only have the gravitational force that is working in the direction of motion. So that is simply going to be mg times hb minus ha, which is equal to negative mgl. Now, the equation for work and kinetic energy is going to be Ta plus the work from A to B is equal to the kinetic energy at B. So if we go ahead and plug in for these values, we're going to go ahead and plug in 1/2 m v0 squared minus mgl is equal to 1/2 mvf squared. Now, unfortunately, vf, final velocity at B, is not something that we know explicitly. But we do know how it's related to the weight and final acceleration that is shown here. So v squared is equal to L times g. So we can go ahead and plug that in, and we can say that, also we're going to cancel out these masses, so we can say that v naught squared over 2 minus gl is equal to gl, which is what our vf squared is, over 2. And now we can solve for v0 because now we have quantities that we all know, the g and the l. So simplifying this further down, we get v0 squared minus 2gl is equal to gl, and this gives us that v0 squared is equal to 3gl, taking the square root of both sides, gives us that v0 is equal to root 6g. And that is the smallest velocity that must be given for the mass to make it all the way up to point B if AO is a rope. Now, if we look at this in terms of, if AO is a rod, if we draw a free body diagram, we're going to have a weight force coming down, but we're also going to have a normal force coming up from the rod that is holding that weight force up. So in terms of Newton's second law, this is going to be weight minus N is equal to ma. Now, if we're going to do this in the minimum velocity case, we're going to assume that the rod actually takes the entire weight force. So therefore, the weight is equal to the normal force. Therefore, ma, which is equal to mv squared over r, is equal to 0 because the weight and normal force are exactly the same. Therefore, we know that v squared at B is going to be equal to 0. This also in turn means that our kinetic energy at B will be equal to 0. So now we can use our kinetic energy argument. We know that the kinetic energy at A is going to be 1/2 m v0 squared. The work from A to B is again going to be mg times hb minus ha, which is negative mgl. We know that TA plus the work from A to B is equal to the kinetic energy at B. We know that this is just 0. So therefore what we have is we have 1/2 m v0 squared minus mgl is equal to 0. We can see that the m's cancel out, and we can actually just solve directly for v0 squared, and that is going to be equal to 2gl. And we see that v0 is going to be 2gl, and we can actually plug in for L, so that is going to give us a v0 of square root of 4g. And that is our final answer.